Hi there. Welcome to part two of the week one learning guide for differential equations. I am Dr. Marissa May. It's a pleasure to meet you. If you will, make sure that you hit the like and subscribe buttons. That way you get notification every time a new video is posted. I'll be sure to put the link to the other parts of week one's learning guide in the description below. That way you can have access to all of them. Also, I'll put a link to the learning guide here if you'd like to print out a copy for yourself and follow along as we're going. That would be probably the best situation. Well, let's dive in. This video is going to focus on equilibrium solutions and slope fields. So looking at our first problem there, we want to consider the differential equation given and the initial point that we are given, and we're asked, is there a solution in an open interval that contains x equals, and I think that should be x equals 4 there. So let's go ahead. There's a couple of criteria. We're going to consider our function to be our differential equation here. So we've got the function of xy is equal to x times the square root of y minus 3. So we have a few questions to ask ourselves. And the first one is f of xy continuous at the point 4, 3? At the point we were given. Okay, so meaning, can you plug in 4 for x? Can you plug in 3 for y and get a value? So let's see, if we put 4 in for x, yes, I'm good with that, and put 3 in for y, I'll get 0 underneath that square root, so I get the square root of 0. So the answer to this question is yes, it is. So we've passed our first criteria. The second criteria, we'll need to do a partial derivative. So we're going to take the partial derivative of f with respect to y. So it means x is going to be considered a constant. So we'll leave x there. We're going to take the derivative then of the square root of y minus 3. So we'll get 1/2 times y minus 3 to the negative 1/2. Or essentially, we'll get x over 2 square root of y minus 3. And now we need to know, is this partial derivative continuous at 4, 3? Meaning, does the partial derivative of f with respect to y exist at 4, 3? Can we plug in 4 for x? The answer is yes. Can we plug in 3 for y? Well, I'm going to get 0 under that square root, which is going to produce 0 in the denominator. So the answer here is no. Okay. Now, here's an interesting point that we need to make. Is it possible that there is a unique solution on this open interval? And the answer is yes. Is it possible that there's not a unique solution on this open interval? The answer is yes. The issue and what we have just discovered is we can't guarantee there is one that is unique on this open interval that contains x equals 4. So we're not guaranteed one. There could be one, but we can't guarantee one here. Let's take a look then at drawing a slope field. These are super fun to draw, but you're going to have to consider creating a table for them. And I'll show you what I mean here. So I'm going to create a table with x and y and then dy dx. Okay. Now I'm going to choose values for x and y based on the points I have here, and then I'll find out what the slope is. So if x and y are 0, then dy dx would be 0 minus 0, which is still 0. Now, a line that has a slope of 0 would be horizontal. So I'm going to take my straight edge. Please don't judge my Sonic gift card here. I'm going to draw at 0, 0 a small line that is horizontal. Okay. Then let me do 0, 1. That would have a slope of 0 minus 1, which is negative 1. Now, when you draw a slope of negative 1 at 0, 1, you're going to have to think about going down 1, right 1. So what you want to do with your straight edge is to take your point 0, 1, line it up with the point down 1, right 1, and draw a small segment. You don't want to connect the points, but you need to line them up so that your slopes are accurate. Let's do one at 0, 2. We would have a slope of -2. Okay, so at 0, 2, you're going to line it up with down 2, right 1, and then draw your segment. You'll notice that your slope is a little bit steeper, right? Okay, let's move away from the axes then. Let's do 1, 1, where you're going to get a slope of 0. In fact, every time x and y are the same, so at 2, 2, at 3, 3, at 4, 4, at -1, -1, right? You're following how I'm knowing that all of these, when x and y are the same, we get a horizontal slope of 0. So I knew that diagonal had to be the same, okay? Okay, we'll do a little spattering here of points. We'll do 1, 0. So 1, 0 would have a slope of 1. So you've got 1 and 0. Now I'm going to go ahead and draw that 1, 0 has up 1, right 1, and line up my slopes. And I'm going to go ahead and graph a few more of these. Okay, so I was able to draw in the rest of the slope fields here with our straight edge and just doing those slopes just like we talked about. Now, realize what the slope field's doing. It's outlining a group of equations or graphs that would satisfy this differential equation, meaning they could be shifted up or down or left or right, depending upon the initial value problem. But this is our slope field that's outlining those. Okay, for our final group or problem for this group for the week 1, we're going to find all equilibrium solutions and then state the stability of those. Now, the equilibrium solutions are pretty easy to find. We're going to take the dy dx and set it equal to 0. And then we'll solve. Let's go ahead and factor out a y, and then we'll factor our difference of 2 squares. So it looks like we actually have 3 equilibrium solutions. I've got one at y at 0, at 1, and at -1. Now that we've found the equilibrium solutions, I want to share with you the slope field so we can take a look at what's going on. I'm going to switch our view over so you can see the slope field for this differential equation. You can easily see the 3 equilibrium solutions in orange, purple, and green. I'm going to be able to move this point because I want you to see what happens as we get close to y equals 1. Notice that the slope tends to get closer and closer to the y equals 1 as x gets bigger and bigger. This means we have an asymptotic stable equilibrium at y equals 1, because as t or x got bigger, then the slope tended to get closer and closer to y equals 1. Now, if we do the same, I'm going to go back to, now let's deal with y equals 0. With y equals 0, you'll notice how as t gets bigger, the value tends to move away from y equals 0. When that happens, we have what's called an unstable equilibrium. Okay, so now we have one more to look at. Let's look at what happens when we get close to y equals -1. So let's move as t gets bigger. Notice how the values tend to get closer and closer to it. And that makes it an asymptotic stable equilibrium. So take a look. I'll link the slope field generator from Desmos below. That way you can use it in your future problems for week 1. As always, feel free to leave a comment if there's something else I can explain or help with. I'll link these below for you. And don't forget to hit like and subscribe. That way you get notification every time a new video is posted. Bye for now.